Hi guys, I want to briefly talk about free fall situations. A free fall situation is defined as a situation where something is moving vertically with only gravity affecting it. We know a lot about free fall based on what Galileo in the early 1600s studied in Italy. And he rolled things down hills with greater and greater slopes and uh, graphed that out and figured out how fast things should fall vertically. And then he also is probably best known for dropping things off the Leaning Tower of Pisa. And his idea was that things that were different masses would fall at the same rate, even though they're different masses. So he would use things that had similar size. So these don't have quite the same size, but they do fall at the same rate. And so if I drop them, they're going to drop and fall at the same rate. I'm sure you heard that tennis ball hit at the same time that the bowling ball did. But so Galileo kind of establishes the idea of the fact that everything accelerates at the same rate. And that's the point that we make in free fall situations. The gravitational acceleration or the acceleration due to gravity is the same. So we know how rapidly things accelerate vertically. Now that's true if we throw things up or if we drop them. So if I throw a ball straight up, gravity is affecting it once it's out of my hand. And the whole time it's accelerating downward. So we're going to learn more about uh, why the acceleration of gravity is what it is later when we talk about gravitational pull and satellite orbits and things like that. But we have the gravitational acceleration at different points on the Earth. Now we treat that as uh, in here, we're going to use 9.8 or 9.81 if we want to go three significant figures. And notice that is the acceleration in meters per second per second. So that means when something is falling, if it starts at rest, 1 second later, it's going to be going 9.81 meters per second downward. 2 seconds later, it's going to be going 19.62 meters per second downward. 3 seconds later, 29.43 meters per second downward. So it speeds up going downward. Now, because we generally treat downward as negative and upward as positive, oftentimes we'll use the acceleration of gravity as a negative value. It all depends on what you decide to do in terms of the sign of things. So if something ends up higher than where it started, we treat it as a positive value. If it ends up lower than where it started, a negative value, that means gravity is pulling it downward. So g, which is our designation for the acceleration due to gravity, is negative. So we use lowercase g to indicate the acceleration due to gravity. That is not gravity. That is the acceleration due to gravity. You'll never hear me call it gravity. You'll always hear me call it the acceleration due to gravity or the gravitational acceleration constant. Notice it's not a constant. It does vary from place to place on the Earth. It does vary from place to place in the universe. So the acceleration of gravity on the moon is about 1/6 that on the Earth. So, but for different places on the Earth, we get different gravitational constants. And we can see there that the acceleration of gravity at the equator is less than it is at the pole. So it does vary. We're going to use 9.81. That's pretty much a universal standard that we use on that. So when we have air resistance, the object that is falling is slowed down by the air. So if we look at this guy on the left here dropping a ball and a piece of paper, the paper has much more surface area, so the air affects it a lot more. If we crumple up the paper, it's going to fall at the same rate as the ball. In other words, each of those images occur when the top image is the same time, the second images are the same time, and the third images where the ball is hitting is at the same time. So the paper still has a little bit of resistance even on the right-hand side. All right. But bottom line is what we do with this then is use the same formulas when we have to do calculations, but instead of A for acceleration, we use G. Oftentimes you'll also see me change the delta x to delta y, because y is what we use for the vertical axis for the Cartesian coordinate plane. So every time you see G or A, you're going to change that to G. And G is equal to 9.81 meters per second downward. Notice we have to have a direction. In one-dimensional motion, usually we'll say negative 9.81, all right? And so we have, anytime we talk about vertical displacement, oftentimes we talk about delta y. We might even designate the fact that the velocities are in the vertical dimension by putting Vy for those. So that's typically how you'll see me do that. You're not going to get necessarily those specific equations with the y's and the and those. You just have to know that A, the acceleration, turns into G, and G is known. So you might get a problem, for example, that doesn't seem to have enough information. Like, how fast is something going when it falls for 1 second? Well, if we know that it falls for 1 second, we know it starts at rest, it falls for 1 second, and we know it accelerates at negative 9.81 meters per second. So we now know 3 variables, even though the question itself doesn't seem to give us those. So we have to imply those other 2 sometimes. All right. So those are our numbers. Notice the distance, the displacement that it measures is different than the velocity. So the left-hand side, the green letters or numbers tell us how fast it's going at each second. The blue numbers tell us how far it has gone after each second. And that's using this formula right here. 1/2 of gt squared. So 1/2. So this is assuming that it starts at rest. So Vy naught equals 0. So when something starts at rest, the initial velocity is 0, so it simplifies all of these. So 1/2 of 9.81 times 1 squared, 1/2 of 9.81 times 2 squared, 1/2 of 9.81 times 3 squared, and so on. And that's where we get the 4.91, the 19.6, and the 44.1, and we can just go from there. One nice thing about free fall motion, and this is a projectile, but it works in free fall as well, is that if we know how fast it's going when it's going upward, it's going to be going same speed, opposite direction when it passes that same level. So there's a symmetry in this. So the thing that we know for sure is that the top of an object's motion, it is not moving up or down. So its velocity at the very top of its motion is 0. So sometimes you might have situations where you're asked, how high does it get? Well, you make your final vertical velocity 0. And if you're asked how far does it drop, and if the word drop is used, usually you assume that it starts at rest. So your initial vertical velocity is 0. So if something is thrown downward or thrown upward, the initial vertical velocity is not 0. It could be positive if it's thrown up or negative if it's thrown down. But we have this symmetry that shows us that at the same level, it's coming down at the same speed it went up. So if I can throw something up at 50 meters per second, when it comes down, it's going 50 meters per second when it comes to my hand. This is why it's so dangerous in third world countries, or where you see people shooting guns in celebration, because that bullet that comes out of the gun at the speed that it does is going to come back down at that same speed at a more random location, so it could be very dangerous. So when we talk about vertical motion, there's a symmetry to that, and that's a really important thing. We obviously deal with air resistance in our atmosphere. If we can do this in a vacuum or in on a planet that doesn't have an atmosphere, we can see that things do fall at the same rate. They did this on one of the Apollo missions. The footage is terrible and grainy, but I'll try to find that and post it for you guys. I also have a interesting video from a science show that they did it in a huge vacuum chamber, the biggest vacuum chamber, I'll try to find that and post a link to that too. All right. Thanks a lot. Have a great day.